Hello, Dr. Guo and Dr. Liu. We are Group 3. Today, we are excited to present our team project based on the Kaggle competition, LLM Detect AI Generated Text. In the current era of accessible generative AI, building a reliable detection model has significant practical implications, particularly for maintaining academic integrity and content moderation. The core task of this competition is a binary classification problem. Given an English essay, the model must predict whether it was written by a human or generated by a large language model. At the very beginning of our project, we encountered a roadblock: extreme label imbalance. In the official training set, out of 1,378 essays, only 3 were AI generated. It is functionally impossible for a model to learn useful classification features from such data. To ensure effective model training, we adopted a high-quality external dataset known as DAI-GTV2. This dataset is not only balanced between positive and negative samples, but more importantly, it includes text from over 15 different LLMs such as GPT-4 and Claude, and covers 15 unique essay prompts. This brings us to the core challenge we had to address: distribution shift. In real-world scenarios, a robust detection model must be able to generalize to unseen prompts and unknown LM generators, rather than simply memorizing the training data. To compare how different technical approaches handle these problems, we designed the 2 complementary models. The first is a traditional machine learning baseline, TF-IDF, combined with logistic regression. We extracted a 300,000 dimensional sparse feature set using character and word level n-grams. The main advantages of this approach are its high computational efficiency and clear interpretability, as it relies heavily on surface-level lexical patterns. The second is a deep learning approach. We fine-tuned the DeBerta v3 base language model. Thanks to its disentangled attention mechanism, this transformer architecture goes beyond surface vocabulary to learn deep contextual relationships and semantic coherence within long texts. Once the models were selected, our next crucial step was designing the validation strategy. This is a key highlight of our project. We implemented a stratified group k-fold grouped by prompt name. This means that all essays written in response to the exact same prompt were strictly kept within the same validation fold. This grouping mechanism prevents data leakage. It successfully simulates the unseen prompt scenario in the actual test set, preventing the model from achieving artificially high scores by merely memorizing prompt-specific vocabulary. Moving on to our experimental results and comparative analysis. First, we observed a massive distribution shift. Both models achieved near-perfect local out-of-fold scores of over 0.99. However, on the final private leaderboard, their performance dropped significantly to the 0.65 to 0.67 range. This proves that the data distribution in the test set was heavily shifted from the training set. Under these challenging conditions, the performance of the 2 models diverged. On the public leaderboard, TF-IDF outperformed DeBerta 0.8486 versus 0.7487. Yet, on the truly unseen private leaderboard, DeBerta proved to be far more robust, scoring 0.6708, surpassing TF-IDF's 0.656. While the absolute difference between 0.67 and 0.65 might seem small, when we dive into their confusion matrices, we uncover a fundamental difference in their underlying decision mechanisms. Please focus on the false negatives. The number of AI-generated essays mistakenly classified as human-written. Facing the exact same test distribution, the traditional TF-IDF model missed 394 AI essays. In stark contrast, DiBerta missed only 35. This is a massive tenfold improvement. Why did this happen? Because TF-IDF heavily relies on surface-level n-gram frequencies. When the topics shifted in the private test set, the specific keywords it relied on disappeared, causing it to fail completely. DiBerta, on the other hand, learned generalizable semantic structures and logical coherence. Therefore, even under distribution shift, it maintained a remarkably low false negative rate. Given the different characteristics of these two models, we attempted a 50-50 weighted ensemble. However, the ensemble only achieved 0.6573 on the private LB, which is actually lower than using DiBerta alone. Our analysis for this outcome is straightforward. Ensembling only helps if the models make uncorrelated errors. In this case, the deep semantic features extracted by DiBerta already subsume the useful information captured by TF-IDF surface n-grams. Because both models made errors on similar samples, combining them introduced no complementary advantage. To wrap up, we would like to share our key takeaways from this project. 1. Validation is not reality. High local cross-validation scores do not guarantee real-world performance. In deployment, we must actively simulate distribution shifts using rigorous validation strategies like grouping by prompts. 2. Semantic depth matters. Traditional ML models provide fast, interpretable baselines, but their surface-level patterns are brittle. Deep learning-based semantic understanding is much more robust for real-world deployment when facing unseen LLM generators. 3. Data quality is paramount. The official dataset was unusable. Pivoting to a high-quality, diverse external dataset was the absolute prerequisite for any meaningful model training in our project. Detecting AI-generated text remains an evolving challenge, and future work will likely require even larger models or multitask learning to keep up with advancing LLMs. That concludes the presentation from Group 3. Thank you very much for your time and attention.